Um, okay, so and also apologies if you've heard this talk before. Sunil might have heard parts of this talk at least. So the context for the main question that I'll be addressing is the prototype original ADS CFT correspondence. So consider n equal to 4 SuperYang-Mills theory in 4 dimensions on S3 with UN gauge group. And the holographic dual of this is a gravitational theory on ADS 5 times S5, whose conformal boundary is the same S3 as the one the Yang-Mills is defined on. So I've sliced this ADS 5 to show the interior. And this theory admits black hole solutions. And in particular, it has black holes which preserve 2 of the 32 supercharges of the theory. And these black holes are large in the sense that the area of the event horizon in Planck units scales as n square, where n is the rank of the gauge group when n becomes large. And the main question is, do we have a statistical understanding of this thermodynamic entropy of these supersymmetric black holes? So the natural place to look is 1/16 BPS states in the dual n equal to 4 SuperYang-Mills. And to count them, one looks at this function called the superconformal index, In of tau. So this is like a Witten index, trace minus 1 to the f, with couplings to various chemical potentials, couplings of various chemical potentials to various charges. I'll spell this out very shortly. And the question is, does this index account for the entropy of these black holes? So if you think of this index as a supersymmetric partition function, then the free energy, which is log of the index, does that scale as n square, was one of the questions that was asked. So these questions were first posed in these papers about 15 years ago. And at that time, the answer seemed to be negative. And more recent developments in the last couple of years have brought up a picture saying that indeed the index does account for the black hole entropy, not only the n square scaling, but also the exact numbers at large. Okay, so this is what I want to explain to you in this talk. So in the first introductory part, I just want to spell out the various elements. So maybe I should go fast because this was supposed to be some kind of a review, but I'll just do it at my pace, but please speed me up if it's too slow. So what I thought I'll do is just tell you what the various elements are. What is this index? What are the black holes? And what is the meaning of this expectation? Before doing that, I want to say that this question is not particular to n equal to 4 SuperYang-Mills. The same question can be posed in any n equal to 1 superconformal field theory in 4 dimensions, which admits some kind of a large n limit. And the only difference is that now the theory has 8 supercharges. So the black holes and the states are 1/4 BPS. In fact, this was the context in which the black hole solutions were first found. Okay, so everything else in the slide is the same. The index function, the details are slightly different, but the question remains the same. Okay, so before I tell you about the various elements, any questions about this? Okay, so let me begin with the index. So n equal to 4 SuperYang-Mills has an SU4 R-symmetry group, which has 3 Cartan generators, Q1, Q2, Q3. And in this more general context that I just told you about, and this will be the context I will be using throughout the talk, n equal to 1 CFTs in 4 dimensions have 1 U1 R charge, and then there can be some bunch of flavor symmetries. Okay, so you can write this n equal to 4 in this language where one combination of Qs is this Q, and the other 2 are flavors. Then the theory is defined on S3, so there are 2 angular momenta, J1 and J2. And then in addition, there are other charges of the superconformal group like energy. If you're interested in BPS states, then we focus on one complex supercharge called curly Q, which obeys the following algebra. QQ bar anticommutator is this right-hand side, and BPS states means Q annihilates it. So E is determined by these 3 charges. And now we want to write an index of Q. That means that you should look at the subspace of states which are annihilated by Q. So if you want the quantum numbers, you should look for charges that commute with the supercharge. So any flavor by definition commutes with the supercharge. And of these 3 charges, J1, J2, and Q, there are 2 combinations, J1 plus half Q and J2 plus half Q in the commutant. So the most general index looks something like this. It's trace minus 1 to the f, e to the minus beta q q bar, times coupling to j1 plus half q, j2 plus half q with a chemical potential sigma and tau, and with other couplings to flavor. Now, by the usual argument, Witten's argument of pairing of representations, this object is actually independent of beta. So it's needed to define the index, but it's independent, so I won't write it. In today's talk, I'll not discuss flavors. Everything I say can be generalized to flavors. And to make life simpler, I'll also put sigma equals tau. That's just for ease of presentation. As I said, all the details can be put back in. So here's the simplest non-trivial index in which the puzzle can be posed. So you have in of tau, it's trace minus 1 to the f, 2 pi tau times 2j plus q. Right? Now you write a Fourier expansion of this index, and the Fourier coefficients are called dn, and these are the degeneracies, of course, with a minus 1 to the f. And yeah, before anything else, there's a small sort of confusion of nomenclature. Dn of, so n, small n labels my charges. It's the charge label 2j plus q. So that labels my particular BPS state. Dn is also an index. It's a trace. It's the same kind of trace in the subspace of charge states labeled by that charge. And in of tau is also called the index, and sometimes this causes confusion, at least to me. So I'm going to call dn the index and in of tau the index function. Okay, just if in case I need to make it clear. There's another point here. I put a divided by 3 here. That's a normalization. N here runs over non-negative integers. And this normalization depends on the normalization of your charges. So the R charge, I've chosen a normalization consistent with n equal to 4 SuperYang-Mills theory, where R charges are quantized in units of a third. That's the index. Next, I'll tell you the black holes. So in the n equal to 4 problem, the dual is type 2b theory on ADS 5 times S5. In the more general context, we just consider minimal 5-dimensional ADS 5 supergravity. And this theory has black hole solutions, which are labeled, which preserve 2 supercharges, and they're labeled by 3 charges, J1, J2, and Q. It's convenient to scale out the Newton's constant and define gravitational charges, small j1, j2, q. And today, I will again focus on the simplest situation where j1 equals j2. Okay, I'll call that j. There are still 2 charges, j and q, but in fact, if you look at the gravitational solution and measure these charges, they're not independent. They obey an explicit relation. I've not written it down as a formula, but here I plot a graph. It's completely explicit. And at large charges, it goes, this is j versus q, and large charges, it goes as j square versus qq. So in effect, there's again 1 independent charge, and the entropy of this black hole is n squared times the square root. And if you write it, if you choose the 1 independent charge to be the same one that I chose in the microscopic theory, I can write the entropy as n squared times some function, some entropy density small s of n over n squared. Okay, so the black hole entropy is captured by 1 function of 1 variable, and the index is also captured by 1 function of 1 variable, the microcanonical index. And the main question is, are these 2 equal in an asymptotic limit? Okay, so let me show you what
was n in the gravity side, the small n? Is it the same exact charge?
It's exactly the same charge. So I want to compare it, so I should take exactly the same one. So small n, unfortunately, small here is not the gravitational charge. So big means that they scale as n square. So unfortunately, I've chosen a notation where small n is 2j plus q. That's why I have to divide by n square.
Okay, I see. Thank you.
Any other questions? Okay, so the question is, are these 2 asymptotically equal? And now let me show you what this index function is. Sorry, the entropy function is. So here I've plotted the entropy itself as a function of this charge n. And you see, so I plotted it for various values of rank, n equal to 2, 3, 4. And you see that, you see 2 things. Firstly, in the horizontal direction, there's a growth with power 2/3. So S goes as the charge to the power 2/3. And then here, you also see in the vertical direction, you see a growth with respect to the rank, as you expect, because this is the entropy. So for reference, I've also shown you the entropy, the index entropy of a gas of gravitons with the same charges, and you see that that's very small, and in particular, it does not scale with capital N. In fact, it goes as charge to the half, and it does not scale with capital N.
So
now, yes,
in your graphs, you've used the supergravity formula, even though we're at finite values of capital N.
Yeah, this is just to show you what you expect. Exactly, that's right. Okay. Now, what is precisely the meaning of this? This had confused me a lot in the beginning when I was looking at this problem. So let me just try to explain this. As I understand it, there are two limits. One limit is the larger limit, where the charge and the rank n scales to infinity, such that the gravitational charge nu is fixed. Okay. This is the limit in which the black holes are defined. There's another limit where you hold the rank or the central charge fixed, and you scale the charge to infinity. So by analogy with the two-dimensional situation, you call this the Cardi-like limit. This is what it's called. These two are completely different limits. Okay? Neither of them is a subset of the other. And there's one regime of overlap when both the gravitational charge, so all three, n, and nu, scale to infinity. Okay, so that's the limit. The Cardi-like limit, you can think of that the black hole fills up area space. Okay, it's an infinitely big black hole. All right. Then the last thing I need to tell you to sort of define the problem is what is this index function? So here it is. It's an integral over, yes.
It's probably clear, but just to ask, nu goes to, if nu scales like some power of n.
Yes.
Is there any complication in using gravity or not?
So you mean, so maybe let me answer what I think I understand, but if I don't answer it, please tell me. So nu is defined as some field theory charge divided by n square. So it's in units of n square. Now you can ask, when are the black hole solutions well defined? Okay, and they're defined, meaning when are they under control? And they're defined for nu sort of some fixed number, let's say between 0 and 1 or something like that. So not 0 and 1, 0 and anything. Now, if nu itself goes to infinity, then you get this, you hit this Cardi-like limit. If nu goes to 0, then there's some other singularity.
Yeah,
then you're away from the gravitational.
In the most straightforward way, you would say that nu being any number of order 1,
yes,
independent of n, is when gravity is valid.
Exactly. Yeah.
However, you are going to scale nu with n in order to be in the Cardi-like limit.
If you want the Cardi-like limit, so in fact today I don't want to discuss the Cardi-like limit at all. Partly, well, I'll tell you about it.
Yeah, but just to ask, is there overlap between the Cardi-like limit and gravity or not?
Yes, there is. So this is the limit when you take weakly coupled supergravity and you make the black holes very, very, very big.
Right. So the very, very, very big is energies of order n. And there is no complication. I wanted a reassurance that there was no complication in using gravity when gravity energies became of order n. I think
you're asking,
I mean, it's usually, sometimes when observables theory themselves scale like n, funny things happen. I just wanted a reassurance that that's not the case in gravity.
No, so here the black holes are big, the horizons are weakly curved, everything is weak coupling. Unless you're worried about some infrared limits like hitting the boundary or something like that, it's all fine from the gravity point of view.
And maybe another way of saying it is that as this thing becomes bigger and bigger, it becomes more and more like Poincare patch, and that's completely non-singular, right? Yeah. But just the fact there was an n there. Anyway, yeah, please go. Yes, thank you.
Mm-hmm. So yeah, just assuming some infinite area space, then there's absolutely no issue. Okay, any other questions? All right, so here's the index function. So it's an integral over n by n unitary matrices of the following function. It's an exponential of this infinite sum. And each term in this infinite sum, so there's double trace in every term, and each term is governed by this so-called single letter index. Here I've shown you the answer for n equal to 4 SuperYang-Mills. What this is you take the same trace that I showed you earlier, and you evaluate it in the space of letters, What that means is that the letters are the various fields of the theory. So gauge field, fermions, scalars, derivatives, all these things at some fixed spatial point. So let's say the origin. So this is some quantum mechanical space, and you evaluate the same trace in that space. Then what this exponential does is to sort of make up these letters into words of the theory, or the operators of the theory. And finally, the integral over the unitary matrices, it projects you onto the gauge invariant subspace, the physical subspace. Okay, that's one way of understanding. That's a Hamiltonian way of understanding it. I'm not going to review this. I'll just take this answer as given. This is from these papers. There's also a Lagrangian way of understanding it, in which the path integral localizes onto UN matrices. Right. I want to make two comments about this index. One is that the fact that it's a double trace means that there's a pure two-particle interaction. There's no single particle interaction. And secondly, the fact that tau is naturally complex means that, oops, sorry, it says that my connection is unstable, but tell me if that's the case.
We can hear you.
Okay. So the other comment is that the fact that tau is naturally complex means that the coupling constants of this matrix model are complex. I'll say more about this, about both these points. So this is to be contrasted with, let's say, the Gross-Witten-Wadia model, where there's a real parameter. So this finishes my review of the elements. Any other questions about this?
Sorry, why do you say the couplings are naturally complex?
Yeah, I'll pick up on this. Absolutely, I'll pick up on this in a couple of slides if you want, or well, maybe I should just go ahead and.
I can wait.
Okay, thank you. All right. The brief answer is from the gravitational side. Okay, I'll explain that in a second. So in the last couple of years, there's been a lot of sort of developments, and people have revisited this problem, and the conclusion now seems to be that indeed the index does account for the black hole entropy. There are various threads. I'm aware that this is not the, maybe this is more than the official list of important references in this audience, but you can take this as my personal list. I think all of these are important, and they go to sort of make a coherent picture. I won't talk about all of my papers. In particular, I will not talk about the Cardy limit unless I'm asked. I'm happy to discuss that. And the reason is that I believe you've already heard about this from talks of Sok Kim. Also, that technically I'm going to discuss the larger analysis, and the techniques that I used are slightly sophisticated, but from that, the Cardy limit follows in one line. So I'm happy to discuss either of these 2 points later. So there's been a lot of work on this in the last 2 years. And today I want to discuss 3 questions. So here are the questions. The first one is actually about gravity. So the question is, do supersymmetric black holes contribute to the gravitational path integral? Okay, and if so, how? And the answer has to do with subtle regularization of the black holes. The second question, and this will be the main part of my talk, is how do we understand black holes as large and saddle points of the matrix integral? And if we do so, then are there other phases? And the answer is yes. And there's some very nice relations with functions appearing from number theory. And finally, in the last part, I want to discuss this law that gauge invariant operators are actually gravitons, which seem to be in conflict with the existence of black holes in the index. And this resolution also has relations with nice mathematics of representation theories and random partitions. Okay, so this is my plan. Questions? I'll move on. So let me start with some, sorry.
Just one question. So I thought that the gauge invariant operators like the Schur polynomials and so on, multitrace, combinations of multitraces, they could also correspond to giant gravitons.
Mm-hmm.
and not just gravitons. I just want to make one comment.
Here in this lore. Yeah, thank you very much. Thank you. So I'll try to spell out the lore. Actually, that's something I would like to discuss later. Thanks very much. Yes, yes. So this will be in the very last part of the talk, and please bring this up when I talk about it.
Yeah.
Okay. So then let me start with. Sorry, just to say what exactly I meant. I was in particular I was referring here to a paper by Chang and Yin, which is, I think, I forgot the date, I think 2013, following papers of Shiraz and collaborators, which sort of made this lore into a conjecture, and I'm going to show you that that's incorrect. Okay, so then let me start with this some very basic sort of almost popular level starting point. So why do we expect that the index, the log of the index should be equal to the black hole entropy? Okay, so if you give a popular talk, you'll say, look, there is a Bekenstein-Hawking entropy of the black holes, and by the Boltzmann formula, there should be log of the degeneracy, and that degeneracy should come from the dual SuperYang-Mills theory, and it's some counting function. Okay, so there are many holes in this argument. So firstly, you're assuming some kind of a Hilbert space of quantum gravity, which we know very little about. Secondly, as is well known, why should the total number of states be preserved? That's not a preserved object. It's not a protected object when you move from weak to strong coupling. And finally, if you go the other way, the index is only a lower bound on the total number of states. So why should it be equal to the entropy? Okay. So the very same questions appear in all problems having to do with counting microstates of supersymmetric black holes in string theory. And experience has taught us that a better starting point is the opposite one. We start with the microscopic index. Okay, that's the Hamiltonian definition I showed you. By the usual rules of quantum field theory, that can be written as a functional integral on S3 times S1. Okay. Now this index is protected. And oh yeah, so just to avoid confusion, I'm not, sometimes people get confused when I say this. I'm not talking about the dimension of 116 BPS operators, which are famously not protected. It's just the index of the 116 BPS states or operators. So this is protected, and therefore this I must be a functional integral in ADS gravity or supergravity with boundary conditions appropriate to the index. So namely some kind of periodic fermionic boundary conditions. And so the question is, does the supersymmetric black hole contribute to this functional integral? Okay. And this is a subtle problem. It's always a subtle problem. And the reason is that supersymmetric black holes have this infinite throat. Okay, so again, to clarify, there's one infinity coming from the asymptotic, so UV end of, asymptotically ADS end of the solution. That's always present in any ADS calculation. So this you deal with the usual methods of holographic renormalization or boundary subtraction. But usually black holes, after removing that infinity, have a finite cap in the interior, in the infrared. But supersymmetric black holes have an infinite throat. Okay? So if you do it naively, you'll get a zero contribution to the path integral.
Samir,
so yes.
What is this comment of 160 dimension? Did you mean the number of 116 BPS operators was not preserved, or the dimension? I didn't understand what.
No, just the dimension. I mean, the whole story of the. Yeah. I just want to say I'm not discussing the dimensions. I'm just discussing the number of states. Sorry if that created confusion. I was supposed to clarify it. So some people say that, oh, when I say 116 BPS states, they say, but of course the 116 BPS operator dimensions are not protected. There's a one loop Hamiltonian.
Oh, in n equals 4 Yang-Mills, they are protected, right?
Oh, sorry. Okay. Thank you. But in any case, that's I'm not talking about dimensions at all. All right.
Okay.
Thank you. Okay. Yeah, but so okay. So what I was told, at least.
I think what you're saying is that in a general n equals 1 superconformal field theory, there's only a U1.
Exactly. So in the context that I'm talking about, exactly, the one loop Hamiltonian. Yeah, that's right.
Right. And that's because U1 charges are not necessarily integer valued. Exactly. But in n equals 4, that U1 is part of a not abelian gauge group. The U1 charges are always integer or half integer valued. They can't be renormalized. Okay. So there, at least, there's no issue.
Okay. So in any case, I'm not going to discuss this at all. I mean, that's not my subject. All right. So what's going on? So the reason I emphasize this set of ideas is because after the sort of original papers where the sort of black hole growth was not found, there were speculations that maybe the black hole does not contribute to the index, and that's why I'm not seeing it. And as I said, the same kind of issue arises in other places, and the regularization that you have to use sort of differs. It depends on the details. So in ADS 2 there is one regularization, ADS 3, ADS 4 flat space, and so on. Okay. So what I want to do is to sort of sharpen the ADS CFT problem and rewrite the whole problem as a path integral in gravity, so that somehow the index is forced to. I mean, of course, it's post facto, but it helps to sort of clarify the puzzle. Okay, so an early clue of towards this was given by a very beautiful observation in this paper, who said that the entropy of these black holes can be recast as an extremization problem. Okay, just a Legendre transform with respect to this function I. Okay, with respect to 3 chemical potentials, and the fact that these 3 are not independent, these charges are not independent, means that there's one constraint which the 3 potentials have to obey. Okay. So the authors have various motivations to do this, but so one thing this reminds you of from this point of view is this Gibbons-Hawking principle, namely that the I should be thought of as the action of ADS space with the black hole solution. Okay, so let's go look at that. So you write down the solution and you do standard.
Hello.
Yes.
Samir, sorry. This is about your comment on the supersymmetric black holes, how to define the path integrals. Like, let's say if I take like a non-extremal solution where there is a finite gap, and then take an extremal limit.
Yes.
Would that be a fine argument, or is there some flaw in that?
No, that's exactly what I'm going to do. I mean, that's exactly what is done, and that's exactly what I'm going to do.
Okay.
It's just the details need to be worked out.
Okay. Because for non-extremal things, it's you can define them fine. You know,
Absolutely. That's right. That's exactly the idea.
Okay. Thank you.
Yeah, somehow these details haven't been worked out for all the cases, as far as I understand. So, and it hadn't been worked out for ADS 5. Okay.
Sorry, Samir, could I ask you about this partition function of Zaffaroni and collaborators?
Yes. Mm-hmm.
You give a partition function as a function of 3 chemical potentials, and then put one constraint on them.
Sorry, partition function is I. Is that what you mean?
Yes, I. Yes.
Okay. Let's call. Yeah. Okay. Let's call it I. Okay. Mm-hmm.
Yeah. Okay. Now, if I use, and then you basically, if I understand right, just use usual thermodynamics. Pretend this is a normal partition function. Use thermodynamics and compute the entropy.
That's what they say. Exactly.
Okay. Under this constraint.
Yes.
So I was wondering now, if you have a partition function, you can also compute charges by differentiating with respect to
good.
potential. And if you compute the charges that you get out of this, and you take the space of all these charges under this constraint, omega 1, omega 2, to 5,
yes.
Does this map out the space of allowed charges of supersymmetric black holes?
Of supersymmetric black holes?
Of the known one.
Sorry?
Of the known black holes. You know, there's a co-dimension.
Yeah, so yeah, that's right. So these will all be, most of them will be complex, and then there'll be sort of slices in the space which correspond to the supersymmetric black holes. Yes.
Wait. So so there's this 3-parameter set, and then there is this one constraint.
Yes.
This gives you a 2-parameter set of charges.
Yes.
Gutowski and Rial would also have had a 2-parameter set of charges.
Yeah, that's right. That's right.
So you're saying these 2 sets of charges don't match to each other? These manifolds of charges, because you say you get something complex here?
Wait a second.
So
at the extremum, they absolutely match. The point about this, yeah, is that good enough? That if you actually solve for it and look at the extremum values, then they match.
Excellent. So
this function does something more, let's take the simplest situation where, let's say J1 equals J2. So then there's only one independent charge. Then there's only one independent chemical potential, but it's complex. And then there's a one-dimensional real slice of that where the black holes live.
Okay, but just to be totally sure I understand, there is this constraint in the space of charges, and that, there's a co-dimension one manifold in the space of charges where you have supersymmetric, good supersymmetric black hole solutions, and that is just simply reproduced from this formula.
Now I understand your question. No, you have to impose a condition of reality.
You have to impose a condition of reality. You say you have to take this set of charges and do what it takes for the chemical potentials to make the charges real. Is that what you're saying?
Exactly. So exactly. So there's a two-dimensional space, and then when you impose a condition of charge being real, then you cut out a one-dimensional real subspace out.
And that makes the chemical potential complex in some way. That
the chemical potentials are naturally complex, even at those points. That's right. And this is what I meant by natural. Yes.
But it makes it complex in some way that you just have to do to it in order to get the charges to be real, and then that's right. This curve. It reproduces the J versus Q relationship.
That's right. That's right.
Okay. Thank you.
Okay. Any other questions? Okay, so I was saying how to sort of derive this. So these are the natural place to look for is just black hole thermodynamics. So if you write down this supersymmetric black hole solution and you measure these chemical potentials, just by measuring the values of the fields in the gravitational solution, you find two things. So firstly, at the supersymmetric point, you find that the temperature goes to 0. And then you find that these chemical potentials all go to some fixed numbers, 1, 1, and 3/2. Okay, and this is, so there are two comments. So firstly, this is surprising because that would mean that there is no thermodynamics at all. So these are just fixed potentials independent of the charges. Okay. And secondly, you also, if you just plug in y, you get -1. Okay. So clearly, what you have to do something slightly more subtle, and it's exactly what Loga suggested. And this is what we did. So this is this paper with Cabo, Bizet, Cassani, and Martelli in 2018. So you look at a parameter space of solutions. So a 4-parameter family of solutions are known, which is not supersymmetric or extremal, and these are roughly labeled by mass, charge, and 2 angular moment. Okay, M, Q, and A and B are roughly those things, but in fact, the quantum numbers are nonlinear functions of these parameters. And then you impose the extremality condition. So that's a codimension 1 subspace where the extremality means that the inner and the outer horizon and inner horizon approach each other. In fact, here there's a cubic equation. So it's the outer and the middle one. And then you look at the supersymmetry condition, which is a condition relating charge and mass. And this is also a codimension 1 surface, but a completely different one. Okay? And the black holes are living at the intersection. The supersymmetric black holes of Grotowski and Real and so on live at the intersection. Okay, so it's a 2-parameter family of black holes. Okay? Now, the idea, if you want to get thermodynamics, is to deform from this. And if you want to, so there's an infinite number of ways to deform. And our idea was that if you want to compare the index, you should deform it in a supersymmetric fashion. Okay, so you stick to this horizontal line, go away from it, and you go a little bit away from it, and define these sort of slopes of the chemical potentials when you go away from it. So beta goes to infinity, omega goes to omega star, such that this little omega and little phi are fixed. Okay. So this idea was first presented in this very nice paper of Pedro Silva, that you have to deform away from this point. And then in our paper, we wrote down a general formalism, and also applied this to this problem of interest. And then this has also been used in other places. Okay, so what are these solutions? Well, in the Lorentzian theory, if you are supersymmetric but not extremal, then these are not physical solutions. The solutions have closed time-like curves. But here, since we are interested in the Euclidean theory, these are just some complex solutions as good as anybody else. And they have some finite cap. It's some cigar-like solution. And so you have these solutions, and now you can just write, you can ask what is the on-shell action appropriately regularized at infinity, and you get on the nose this function that I showed you. And then because this is supersymmetric, there's a global regularity condition of the killing spinor. So you have to take an appropriate real slice of the geometry. And when you do that, you get exactly this constraint that was written here. Okay, and this.
Sorry, could I ask? If you deformed away into this branch, which was good Lorentzian solutions, then would all the chemical potentials always be real?
Yeah, so there's one direction. Yeah, so it's probably this direction. There's a direction you can make it real. That's right. Yes, it's probably this one.
The usual physical black holes have real chemical potentials, right?
That's right. That's right.
So it's sort of crucial that you're deforming in this other direction.
That's right.
Okay, and in this other direction,
the justification is just supersymmetry.
Okay. Okay, and in this other direction, choosing the particular complex value of the chemical potential is done, as you said, just to get real charges.
You mean at the end of the day to get the black hole solution itself? So yes. What you can do is if you go here, right, and then just take the limit, then of course you get what you get. You get the black hole itself. So maybe I misunderstood your question. So over here, for instance, if you calculate what the charge is, it's complex. But at this point, you get a real charge.
Right. I was thinking the following. As you said, there are these chemical potentials that become frozen.
Yes.
Okay. But there are the deviations from them that are physical, right?
Yes.
Which basically
becomes zero here. Yes.
Which had the interpretation of once multiplied by beta, they're non-zero.
That's right.
And these are the true chemical potentials in your problem, right?
That's my claim. Yes. Mm-hmm. I didn't hear the last thing you said.
Effectively, the values of the gauge fields, at least for normal black holes,
exactly.
would be the values.
Exactly.
Right. So those presumably in your solutions could be arbitrarily complex.
Yes.
And then you have to choose what complex values they take in order to get real charges. Is this right?
That's correct. Yes.
Okay. Thank you.
All right. Now, where was I? Yeah, I was saying regularity condition. Good. And this right-hand side of this is interpreted as the Wilson line, as a background R symmetry Wilson line at infinity, which is needed for supersymmetry. That's one way to understand it. It's a cigar. So fermions naturally have one spin structure, which is anti-periodic. And if you want to make it periodic, you need to turn on some background Wilson line. And that's exactly what this is. Okay. And now you have this constraint. You can solve for phi, and you get a function only of omega 1 and omega 2. And I'm going to set the two to be equal in the rest of the talk and call it 2 pi I tau. And I get this action here. Okay. This I is not the index. I is in the exponent. It's like a free energy. I for Euclidean action of radius 5. And there's an n square divided by 27 times pi I times the simple function cubic divided by quadratic. Okay. Now, there are two comments, and this was sort of the answer to the question that Shiraz was asking, namely that, so firstly, because you embedded this, so let me back up. So what have we achieved? So what we've achieved is you took the problem of the microcanonical entropy of the black hole, okay, at the horizon, which is defined at the horizon, and embedded it in asymptotically radius 5 space. Okay, so there we say that the answer is just the on-shell action of this appropriately regularized radius 5, and because that approximates the path integral at large n, the radius 5 path integral should be equal to this, the canonical partition function. That same argument shows you that this tau parameter is actually the geometric parameter of the CFT background. So that's some S3 times S1, and the tau tells you how there's some sort of twisting. And if you evaluate it as a function of the charges, this we've had a lot of discussion, so I won't say it more, then you get it to be naturally complex. Okay, now. Sorry?
There's presumably some constraint on the real part or imaginary part of your tau so that this index is well defined, right? So that it doesn't blow up.
It's in the upper half plane.
And you see that also from gravity, that all your solutions have tau.
Yes. Exactly. So in fact, this was the hint. So when we looked at this black hole, you can just say, where does tau live for this black hole? And it's some sort of so what it is for sorry, I'm just going to open and close a parenthesis. In flat space, for instance, in 4-dimensional flat space, you can ask similar questions. And oftentimes when black holes don't rotate, then you have some pure imaginary value of this tau. That's I'm just giving you the normalization in which it's done. It's the upper half plane such that the pure imaginary values are relevant for non-rotating black holes usually. Here you see automatically that it's not on the y-axis. That's what I mean by complex.
Yeah, thank you.
Yeah, all right. Okay, now, so at a philosophical level, I've done this. So the reason I did all this is to sort of embed this problem into ADS 5 CFT4, but practically it's also very useful. Any problem that I can pose with about dn, the microcanonical object, can be equally well posed for the canonical function. Okay, I remind you what it is, and from now on, I'm going to do a change of variable tau goes to tau plus 1. This is not at all necessary. It's just to make the formulas fit better. Okay, just a technical, presentational trick. So this question of whether the microcanonical microcanonical degeneracy equals the entropy is completely equivalent to whether the free energy equals this particular function that I showed you. Okay, and at a technical level, one reason to do this is because oftentimes these canonical things are easier to compute. You also see that it's a much easier function. S, I didn't even give you the formula because it's a complicated formula. This is a very completely simple rational function. And the limits that I talked about have analogs in the canonical picture. So the Cardi-like limit is simply tau goes to 0 at fixed n, and the large n limit is just n goes to infinity at fixed tau.
So, Samir?
Abhijit, yes.
One question. So, in the black hole calculation, the gravity side, the -1 to the f was put in because you had 2 pi I on the right hand side of the constraint. Because you said something about fermions, this spin structure and so on.
Yes. That's
so right. This is expected even with the -1 to the f, right? This is that because that is incorporated here.
Yes.
Okay. Thank you.
Yeah, that's right. So I'm going. So the philosophy I'm taking is that it's the same quantity you're calculating on both sides, and therefore they must agree. Of course, there are many subtleties to this statement, even things that I've not said, and if they come up, we can talk about it. All right. Now, since Abhijit raised the question for experts like you, notice that the fact that the action goes as 1 over tau square as tau goes to 0, if for some reason, like me, if you thought that there is any modular form behind this system, the answer is it cannot be, at least in any naive sense, because you have 1 over tau square and not 1 over tau. Okay? So in other words, this is not the partition function of any 2-dimensional CFT. All right. Now, however, later I'll make some comments about modular. So that finishes my introduction, which was supposed to take much less, but I also had many questions. But please tell me if there are any other questions.
So when you are asking about this log I and tau tending to this, you want to ask this in the large n limit, right?
So you can ask both questions. Today so I had one paper about this in April 2019. That was the Cardi-like limit. So in our first paper with CCNM, we did this gravitational analysis. In our second paper, we did the Cardi-like limit. Then there was a paper with Alejandro where we did the large n limit, and that's what I want to focus on.
So in the Cardi-like limit, why is this expected? Because all the calculations so far were semi-classical gravity calculations.
I agree with you. So there's a regime of overlap where the black holes become very, very big. So in that, so it's still expected, but it doesn't mean that you've solved the full problem. Is that fair, or you think it's not even expected? So you take a black hole and just make the black hole very large. It's like what Strominger and Waffa did.
Okay. Okay. Thank you.
All right. I hope you're not concerned with time too much.
No, not.
Okay,
not,
thanks.
Not too
I mean,
much.
I had prepared for exactly little less than 1 hour, but if
Yeah,
I'm not under
that should
pressure
work well.
to finish on time, I'm much happier.
Yeah. That's fine.
Okay. Of course, if anyone wants tea or something, please. No. One good thing about the Zoom forum is that you can always do that without anyone being offended. Okay. Let's move on. So now the rest of the talk will be about the matrix model. Okay. So these were the expectations from gravity. And so first, I think this is not chronologically the first thing. This was in my paper in May, but I think logically the first thing to do is to just look at data of the microcanonical entropy. So here I plotted log of the absolute value of this degeneracy as a function of the charge n for various gauge groups, U2, U3, U4, up to U10. And the solid lines are the expectations from gravity. These were the curves I'd shown you earlier. And the dots are the data from the Yang-Mills theory. Okay. So you see many things. So the obvious thing to see is that there's a very good match. So the Yang-Mills theory really sort of follows the expected curve, even at very small n. Okay, so Abhijit, the comment that you made that one has no right to expect it is correct, and there's something surprising here which I think hasn't been completely understood. I have some ideas about this, but I can discuss this after the talk.
Okay, thank you.
But notice that at small n and small charge, there's still a wonderful agreement. The second thing to notice is that there are these oscillations. I think it's best noticed for n equal to 10. You see that there are these oscillations around the black hole entropy curve.
Sorry, this small n, can you remind me, is it in the units of n squared or just units of 1?
No, so the small n is just charge.
Oh,
and,
okay.
Right, so you have to divide. So if, for instance, here, it's, it's 50 or 70 or 100 divided by 100. So it's actually 1. So it's perfectly fine as it,
Yeah, okay, I see.
All right. Now, there are these oscillations, essentially periodic oscillations. Okay. So that's the second thing. This I won't explain. Actually, now I do understand this, but this is not yet in any paper. So I'm happy to talk about it after the talk. It's actually very beautiful. And it's related to these questions of reality that Shiraz was asking. But I don't want to discuss this now unless it's really pressing. And the third pattern is, the third observation is that before the points latch on to the gravity, there is a bit of something else is going on, and you can see that most clearly in n equal to 10. So there's something funny going on, and then it latches on with periodic oscillations. Okay, this I will explain towards the end. What happens at very low charge? All right. So in the rest of the talk, I want to tell you about my analysis, the larger analysis of the matrix model. So any questions about the data? Any other questions? All right. So here's the matrix model. So you do the usual thing. So you write U in terms of its eigenvalues. So the eigenvalues, it's a unitary matrix, so they live on a circle. I'm going to call these phases small ui, I'll call them eigenphases, and write the integral in terms of those eigenangles or eigenphases. And what you do is you take this matrix measure.
Sami, just to pull you back to the data, you plotted the modulus of n. If you also kept track of the sign, I believe, if I understand right, there's a rapid oscillation at the beginning and then more complicated oscillations at the end. Is that? Can you tell us about the signs?
I can tell you. It'll take a bit of time. Maybe I'll tell you verbally now, and then maybe later I'll pull out my notebook and show you something. Is that okay? So that's not quite correct what you just said. There's a very clear picture. So you take d of n. So first, so here are the experiments. Take d of n, divide it by the black hole, this black hole entropy. Okay, so that you get rid of this exponential group. Okay, then these questions you can see much better on a computer. what you see is your computer just, the graph just gets filled. It's like a blur of points. Okay, if you plot d of n, this ratio as a function of n. Typically, what that means is there's an interference. So now what you do is you plot d of n, I mean this ratio, but you twist it by cube roots of unity. Okay, so in other words, you just plot it for n equal to 0 mod 3 or 1 mod 3 or 2 mod 3. Okay, the 3 because of the quantization that I discussed earlier. Okay, then miraculously this clears up and you get oscillations, perfect cosine oscillations, which are macroscopic. Maybe this is what you meant, so apologies if I said it's not correct. Maybe this is exactly what you meant, but it's not a first or a second. It's exactly this. There is some rapid oscillation. If you get rid of this, then you get this macroscopic oscillation, and that has a very clear explanation. But in order to get the explanation, I need to tell you this my solution of the matrix. And when you, so there's some unpublished work I have, which is if you look at what I'm going to tell you and sort of superimpose it, you really get on the nose this what you expect. So there's not even any gaps that you see here anymore, except at very low charges.
Okay. So this rapid oscillation of you said with the periodicity 3.
Yeah.
That is reflected in a chemical potential, imaginary part of a chemical potential, which is like 2 pi by 3.
Yes, exactly.
And that's what you expect from black hole physics. Black hole physics gives you that. Okay, and then the imaginary part is corrected by something larger, and those are the remaining oscillations.
That's right. That's the interesting thing. That's interesting. Okay, so that's something we've not seen in Schrödinger or any other black hole that I know of. Okay, and those have scale, which is so. By the way, thanks for your questions in the last meeting that we were at. That's what prompted me to do these calculations. Those have a scale which is actually essentially the same scale. It's n to the 2/3 or n squared, depending on how we measure it. Let's talk about this later, please.
Okay.
Okay, but it's a macroscopic scale.
Yeah.
By the way, Samir, if I remember correctly, don't Kim and collaborators in one of their recent papers talk
they
about
also have, that's right. So I should say that. So on the same day that I wrote this paper, there was another paper by Agarwal, Kim, Hong, and one more person I'm forgetting. Apologies. And so they also, so I didn't explain this in my paper. They do address this problem. Yeah. I think what I'm going to say to you later privately is not in any paper. Alejandro, actually, he explained part of that to me, and then I also did some calculations. But part of what I will say was there in the paper. Okay. All right. Whoa. All right. Let's go on. Now, where was I? Good. So you write this matrix measure in terms of the flat measure of the eigenphasors, and what you get is the following. So remember, when you do that, you have some kind of a van der Monde determinant, which is a two-particle interaction, and now the action is also a two-particle interaction. So you just get in this flat measure of the eigenphasors, you get an action which is purely two-particle. Okay, so this is what I emphasized. And now remember that these eigenphases go between 0 and 1, and they're periodically identified. So imagine you have a circle and you have n particles with the same two-particle interactions, all governed by one function v, either a repulsion or an attraction. Then, essentially the only thing you can think of, but maybe there's something more sophisticated. The first shot would be that there's a uniform distribution, that they're all equally spaced. And there's another obvious solution where all of them clump up to one point. That solution, you can check that the index itself vanishes at that point, and it's singular. So I'm going to sort of excise that point. But then you have this uniform distribution. Now you can calculate the action of this uniform distribution along 0, 1, and what you find is that the action vanishes to leading order in F. Okay, this is consistent with the earlier papers. Now, so I made this point that there is sort of, from the gravity point of view, tau has to be naturally complex. And if that's the case, the sort of natural thing to do is to say that the fields also must be complex if you're looking for saddle points. Okay, that's what we usually do. And this is what we did in this paper with Ali Khan. So in order to discuss complex fields means U. So this is the U plane. So this is the original contour of integration. You have to ask, how do you continue the action into the complex plane? Okay, so often people do an analytic continuation. That's not what we will do. We will. I'm going to do a continuation in such a way that there is a double periodicity with periods 1 and tau. It's already periodic with 1. I'm going to give it another periodicity with tau, so that the whole thing is defined on a torus. Okay. And then the statement is that the uniform distribution, so that intuition remains the same. The uniform distribution along 0, 1 is so first I find that there's a family of saddle points. So here I have a torus or equivalently lattice. Every lattice point gives me a saddle point. One lattice point is the same as some arbitrary mn winding cycle on the torus. And then the A cycle gives me the entropy of pure ADS, and the B cycle gives me the entropy on the nose of the ADS5 black hole.
Sorry, Samir, I messed this up. If you do an analytic continuation, I can imagine that the answer to the undeformed problem and the answer to the deformed problem are the same because of some use of Cauchy's theorem.
Yes.
But if you do a deformation that's not analytic, what is the relationship between the answer to this question and the original?
Okay,
question?
so I'll answer that in one slide if you allow me.
Okay.
That.
Yes, please.
Okay. Now, so those are my results. Now I'm going to, the next few slides are explanation of this result. So let's start with the lemma. We'll start with an action of this type, that you have one potential V, so exactly of the type that I just said. And that this potential is even, that's the case for us, and it's periodic with some period tau, and tau can be complex. Okay. Now you have to write the saddle point equations at large n, which are just du of s is 0 and du bar of s is 0. These are different equations. So because we don't have holomorphy, we have to solve two equations. So here is the lemma. The first part is that the uniform distribution of eigenvalues between 0 and the period is a solution of the variational equation. Okay, this is a very easy thing to show. It takes 3 lines. It's a homework exercise. And the second part of the lemma is that the action of this distribution is just equal to the average value of V along that uniform distribution. Okay, this is also a very easy exercise. Maybe it takes 3 or 4 lines instead of 2. Okay, both of these can be checked very easily. Now to the question that Shiraz just asked, because your action is not holomorphic or meromorphic even, you can't just deform the contour. Okay? And what happens, so this has to be answered in the context of this particular problem, or at least that's the only answer I have. In this particular problem, what happens is that so you have some original contour of definition, and the saddle point that I'm talking about lives somewhere in the complex plane. So if your action were meromorphic, you could just deform it, and because of Cauchy's theorem, make it go through the saddle point. Now you can't do that. However, what happens here is that if you draw 2 contours. One is the original one, and one is a particular contour which goes through this complex saddle point. This we did in the paper. And then you show that on that contour, on both those contours, the action is actually equal to the value of a meromorphic function. Okay. Therefore, you start with the original contour definition. You make it into a meromorphic function, you deform it, and then you use the observation that I just said to read off the answer. Okay, so that's how this is justified.
Sorry, Samir, I didn't quite understand the observation. What was the observation?
The observation is that on the saddle points, the value of my deformed action is the same as the value of a meromorphic action. And the meromorphic action is nothing special. It's the original. So if it is simply the analytic continuation of the original.
I see. So it's just that it's not quite a saddle point of the meromorphic action, but it is equal, the value is the same.
Exactly right. So because the fact that you just said means that, that's why you can't just solve the, you don't, if you solve the original action, you don't find these as solutions. Yeah.
But I still haven't understood. Sorry. So if I just use the original action, this would not be a saddle point.
That's right.
So you can deform to this contour, but why is that the sort of dominant contribution now? It sounds like
so I'm not making claims about dominant contribution. So I'm just saying that this is a saddle point, and I'm telling you why it contributes to the thing. Now, what we also showed in the paper is that along the contour, the usual saddle point, the contour that we constructed, the usual saddle point analysis holds true in the sense that what I said about the two actions being equal holds not just at a point, but at a width such that when you scale large n, you actually get the full Gaussian contribution.
I see. So I'm just to understand the logic. It seems you use the path, the integral along the original contour of the original matrix model is the same as the integral along your new contour in the analytically continued matrix model. That is clear.
Yes.
But now you also want to argue that this equals that the integral along this new contour of the deformed matrix model is the right answer, right?
Yeah, so let me just spell that out. So the first step was that exactly the integral on the original matrix model is the same as the integral on the new contour of the analytic function, the complex analytic function. And the second statement is that the integral along the new contour of the analytic function, the full contour, is the same as the integral of my deformed function.
Okay, but
and the third statement is that that's a saddle point of the deformed function.
And that third statement is what justifies saying that it's a good approximation to the answer.
It's the three taken together. You can just you can check that. So I should point out that in my paper so far, and also in all private calculations, this uses the large n limit. So in doing this estimation, there's a subtle estimation where you have to show that not just at that point, but around that point, the two functions are equal. Now, the question is how much around that point, because you're going to scale n to infinity, and that thing should go to 0. And you have to show that that doesn't go to 0 too fast, because otherwise you don't pick up this point at all, and you can show that that happens.
I see. So suppose I were to produce some other function which was also not analytic, and that would also give me the right answer in some. I haven't quite understood the argument, but we'll go on. I'll ask you at the end.
Okay. All right. Yeah, it's not easy to find saddle points, by the way, as you know. Yes.
Samir, yeah. So I mean, usually when we look at the saddle point, we look at the saddle point of the analytic function because we are interested in a path of constant phase, right? So that rapid oscillations are not there.
Very good.
So if that is not the path, because this path is being found with a different kind of function, not an analytic function. So this path will not have the property of having no rapid oscillations.
Very good. So this was
nevertheless a saddle point approximation is being used, right? So even though the action were to agree, it doesn't seem a reliable thing because of rapid oscillations still being present on the new path.
Yeah. So let me just answer that. So this is what I was trying to say. So what we showed in the paper is that it's not just so imagine it's a one variable problem. So okay, you have something like that. So usually the rapid oscillations, what do you do in a saddle point? You say that's the point, then you approximate by Gaussian, and you turn it around such that there is no oscillations, right? In the most sort of least steepest distance.
Yes. What
I'm saying is you can do that also for this problem. What you don't have control over is the rest of the contour. So in principle, it could be that there are lots of things going on there which actually dominate the integral, but it doesn't seem to be the case. Usually the assumption is that the Gaussian just dominates the whole thing. That assumption I'm still making. I'm only doing it to 2 derivative level, not higher. But up to that level, it's exactly it's what you said, that you have to make sure of that, and you do make sure of that.
I see. So you're saying in the region that dominates the integral, this property of having no rapid oscillations is still there.
That's right. Because
the rest of the region anyway doesn't contribute. So
that's an assumption which I'm making.
Okay.
Thanks for pointing that out. Yeah. So
Thank
for that, it's important that you satisfy both these equations separately.
Okay. And are you going to say what this action is, which
Yes,
is
that's what I was going to do next. So let's do that. So here's the action. So this is the original matrix model.
Just let me ask once. It shouldn't worry us that this path was not a saddle point of the analytically continued action. If I just did saddle point approximation on the analytically continued action, I'd get some different saddle points, right?
Yeah, there is something to be understood there, which I don't understand. I agree with that.
Okay, thanks.
So yeah, this is the best of my understanding what I just told you. Okay. So here is the index. Sorry, there's one more comment to make about the. Okay, so since you guys said time is not so important, let me just make that comment. The comment is that if you now start looking at small tau, before you start looking at small tau, what you find is that a lot of this is unpublished, by the way. If you take tau very small and you ask what happens to this distribution, that's the black hole distribution, you find that actually even to the original analytic function that I was just about to present, there is a saddle point of this type, but it's not uniform. So at least in the small tau limit, but small but not 0 tau, there is a certain distribution that you can numerically find. It's a solution to a certain equation, which gives you the same action. So that's another piece of data I have. Okay. And then I believe that there is some Q deformation that should take you from one to the other. All right, let's go on. Here is the analytic function. So this is fairly well known. The action can be written in terms of these what are called elliptic gamma functions. Despite the name, these things are not elliptic. They're only quasi-elliptic in the sense that they're periodic along period 1. Here is the function, but not along tau. Right? But the lack of periodicity along tau, when z goes to z plus tau, is very simple, and it's completely captured by this function, which is the odd Jacobi theta function divided by Dedekind eta function. Okay. So now I'm going to tell you what I did. There's a certain motivation for this, which I did not include, but I have as a backup slide. If Abhijit, if you want, or anybody else wants, I'm happy to talk about that later. Let me just tell you what we did.
Sorry, this function does seem analytic. I didn't quite see the non-analytic.
This is the original function. This is the original function.
Yeah.
I haven't yet done my definition.
Okay.
So here's my definition. So what you do is you construct this function q as follows. You do 1 over gamma. You want 1 over gamma, but instead you dress it up. You dress it up by theta naught to the power z2. Z you project along 1 and tau, and times some Bernoulli polynomial in the exponent. Okay, so this is manifestly not meromorphic. Z2 is the imaginary part. And then you observe the following. So if you ask me why I did this, there's a small story to that which I can tell you later. But let me tell you what happens. Some very nice things happen. So firstly, on the original contour, these two agree as they should. You engineer it in some sense such that it's doubly periodic. So when the lack of periodicity of gamma is theta naught, and therefore when z2 goes to z2 plus 1, there's an additional compensating theta naught such that it's compensated, and this is also needed for some reason, such that the absolute value of q is doubly periodic. Okay, and now here's the surprise. So far it's sort of engineering, but here's some beautiful mathematics, namely that this function happens to be something very beautiful, namely that it's what is called a period function. All that means is that it wants to have modular properties. So the left-hand side of this equation, if this were a sort of Jacobi type form of weight 1 or something, this would be 0. In this case, it's not 0, but what it is something very nice. That's called the elliptic dilogarithm. This was first sort of discovered by Bloch and Wigner. So this is neither our Bloch nor our Wigner. They're both number theorists. It's a very beautiful function. This is not how they wrote it at first, and then the generalizations by Ramakrishnan. This formula, so there's a lot of mathematics literature on this. It's a very nice paper of Zagier on this. And the fact is, if you don't care about such things, that the right-hand side has a double Fourier expansion. It's a periodic function, W periodic function. You can ask what are the Fourier exponents, and here's the formula. So here you can see manifestly there's a double periodic expansion, and the exponents are just given, and that's like an Eisenstein series, if you recognize that, of weight 1, 2. Okay, there's something nice. And again, if you don't care about that, this is useful because if you take the imaginary part of this equation, then you just get a Fourier expansion for log of tau, or log of q, okay, which is what you need. So if that went past very quickly, I'm just summarizing what we did. So we deformed the action to a doubly periodic function. So the new action reduced to the old action, as it should, on the original contour. And the fact that it's doubly periodic means that now I can apply my lemma. Okay, and therefore there's a family of saddles labeled by m, n. The GCD condition is to avoid overcounting. And the action of this saddle, which is actually quite a difficult, so if you do this in other ways, is that this turned out to be quite difficult to do, to calculate the action of the saddle. But here, this Bloch formula, by the way, this is called the Bloch formula. It's a very important formula in number theory for various reasons, which are apparently deep. The Bloch formula just gives you a Fourier expansion. So because of my lemma, you just have to read off the Fourier coefficient, and it's a 3-line calculation. So here's the action. So the action of m, n is this n squared divided by m times this rational function. And for 1, 0, you get exactly this function that we saw in the context of gravity.
So Samir, is it crucial here that you are working with sigma and tau equal to tau?
Yeah, so well, I don't know if it's crucial, but this is what I've done. I believe you can, Francesco Benini had a paper where he does this beta ansatz story where sigma minus tau is a rational number or something. I think all of this can be repeated for this. I don't know whether it can be done more general.
So in relation to that, the saddles that you get, maybe you will say, are they related to the solutions of the beta ansatz?
Yeah, so the answer is yes. That's it. It's a small answer. The answer is just yes.
Okay.
Ask me questions if you want. So there's a one-to-one map. I don't know why there's a certain confusion about this in the community, but what I do, you basically the saddles are just labeled by m, n. The saddles of the beta ansatz are also labeled by m, n. This is not an exhaustive set of saddles. Maybe that's where some deep confusion, but I believe this is sort of the main family of saddles. In our last paper with Alejandro and David and Dario, we also wrote a much bigger set of saddles. I believe that every saddle of this will be a saddle of beta ansatz and vice versa. So one of the things we did in our paper with Alejandro was we wrote like some huge appendices where we checked that the action, so in the beta ansatz approach, for instance, the action is not very easy to compute. And in the papers of Benini, they had only discussed this 1, 0 and 1, 1 type of saddles. So we immediately noticed that the saddle point configurations are the same. They're just uniform distributions. And we went through some pains to show that the action is also the same. And I believe there's a more sort of less calculational way to show it, but I don't have it here.
Okay, thank you.
Sorry, there are all kinds of subtleties to that. In the last couple of months, people have been finding some continuous solutions. I'm not talking about this thing. I'm just talking about this family that I just showed. All right. So here is the action of the black hole, and notice that as tau goes to 0, clearly this one dominates. So what I'm going to do next is to try to draw a phase diagram. So first, let me tell you what I did. So all I did was to say here is the complex tau plane. And I just choose a value of tau, and I have a whole bunch of saddles m, n. And I just ask the computer to tell me which one dominates, whose real part dominates. And the answer, so I've cut it off at the imaginary tau equals 0.1. The answer is that at large values of imaginary tau, it's pure ADS. When you start going towards the real axis, you start seeing these new solutions. This one is the black hole solution. The whole problem is actually has a symmetry along the vertical axis, which in my coordinates is minus 0.5. And so you see this mirror picture, mirror black hole. Now, what happens if you go further down, and this is where the fun starts, you see that near every rational point, m comma n, there's a new phase which dominates. Okay, so there's a very rich structure of saddles, okay, which dominate near those points. Okay, so this is some type of phase diagram. But let me now give you some comments about this. So far my index formula looks something like this. Okay, it's like a physics formula. You sum over all saddles, e to the minus of the action of the saddle, effective action of the saddle.
Sorry, so Samir, does this give you a prediction for what?
Sorry, I can't hear you.
Does this give you a prediction for what range of tau the black hole dominates over?
Yes, absolutely. So naively it's this, but I'm going to tell you one more thing, where there's a small subtlety to this, but the answer is yes. It's here. I'm going to slowly move my cursor. It's like this.
And is that the same place where the Hawking-Page transition happens?
The Hawking-Page transition lives on is on the edge of this, meaning on one point of that's right. So there's a small subtlety to this. Let me just say that, and then I'll on this picture the answer is no, but that's because this picture is slightly naive and it has to be corrected just a little bit. I'll tell you what the correction is. So that's exactly where I was getting at. So here is the sum over saddles. Now, this by no means is an exact formula. Alejandro has some work which is going to appear, which promotes this to an exact formula. But it's not an exact formula for many reasons. Firstly, I haven't found all the saddles. It's just one family of saddles. Even if I did have all the families, I have to make sense of this infinite sum. Okay, I don't know if this is convergent. Thirdly, even if that didn't bother me, I don't know how the function behaves as a function of tau. There can be, I mean, this is where all your questions were also heading towards. You have to, if you really want to do the analysis, then you have to look at the space of contours. You have to do some Picard-Lifshitz theory and ask you what is the dominant contribution at a given tau. There might be wall crossing. I've not done any of that. Okay? However, the fact that I can tune tau and at special points, one phase, each of these phases dominates, leads me to believe that all of them are actually physically relevant. One more, the fourth subtlety about this formula is that when two or more of these mn phases have the same real part, right, then again you have to correct the formula, because then it's important to take into account the subleading contributions and the phases, because then there can be interference. And this hits all the questions, many of the questions that were asked. So in particular, if you look here, it turns out that this black hole and its mirror actually have the same real part of the action. And so you have to correct this picture a little bit. When you do that, what happens is that this thing here goes down like this and actually covers here until 0.5, and then the Hawking-Page point sits there. Okay, and this is also the reason, since we're at this is also the reason for the macroscopic oscillations. You have two phases with equal real parts, both are of order n square. So if you now want a microcanonical answer, you're getting contributions from both, and therefore there's a macroscopic oscillation. The phase is also of order n square. And that's what I see in these graphs that I didn't show you. Okay, but it's a very simple answer. Now, did that answer your question, or is there something else? Shiraz?
Are you asking me?
Yes, I asked you because there were two questions you asked me which I left hanging. One was the oscillations, and one was just now about the Hawking-Page.
The oscillations, this explains the slow part of the oscillation. Right?
Yes.
The rapid part of the oscillation is something else.
That I already explained. That's just a fact that there is a
chemical potential has a pi by 3 or something. 2 pi by 3.
Yeah.
But so this phenomenon also reflects itself in some correction to the imaginary part of the chemical potential, some small correction.
The rapid oscillations.
No, the rapid oscillation is a chemical imaginary part of the chemical
potential. Right. So that let's get rid of. The macroscopic oscillation is not small. It's actually a very big, and it's a phase. But the exponent of the phase is of order n square. It's as big as the real part. That's why it's a macroscopic oscillation.
But it oscillates really over charges that vary over n square or some lower power of n.
So I don't have the answer to this, but this is just a small calculation which I should have done before the seminar. I didn't. But so the only reason I'm hesitating is that If I factor out the gravitational charges, then it's n square. So the answer, yeah. So it's the same n square that you see in the real. If you think that the real entropy is of order n square, then this is also n square. But if you write it in the small n units, then it's n to the 2/3 times big N to the 2/3. That's why I'm hesitating. That's all.
I see. So it
It's
has
exactly the
macroscopic
same.
equality.
Yeah.
Yeah. Okay. Excellent. So excellent. Thank you.
Okay. Now these are the comments. So in particular, we also define these new Cardy-like limits. Remember, the Cardy limit actually is a little bit subtle because tau is complex and the charge is real, right? So Cardy limit, usually you say when a charge goes to infinity, energy goes to infinity, tau goes to 0. But if you're more careful, the correct statement should be that imaginary part of tau should go to 0. Okay.
Sorry, Sami, could I follow up just one? When we have normal entropy functions, which are n squared times a function of charge by n squared, that leads to chemical potentials that are order 1. So here, the scaling you explained would also lead to an imaginary chemical potential of order 1. Is this right?
Yes.
So would this be a correction to the other order 1 chemical potential?
No. The correct, it's in the microcanonical. So everything in the canonical picture is just exactly like you said. When you do the Fourier transform to get the microcanonical entropy, that's where you see the oscillations. There, it's just that there's an n square multiplying the whole thing. That's all it is.
Yes, but that's just the.
Sorry, I can't hear you.
If I went from microcanonical to canonical, I can get chemical potentials by some derivative of the entropy, right? So this would give you chemical potentials order 1, just like it does for the real part, right?
Yes.
So this would contribute some imaginary part of the chemical potential, which is order 1.
That's correct.
Which would seem to be a correction to this imaginary part of the chemical potential, which is 2 pi by 3, which you already told us about, which was also of order 1. So I was wondering whether these two compete with each other.
No. This the first part of your statement is not order. Sorry, just give me a second. I was actually doing these calculations 2 days ago. I can try to do.
Yeah, that I think is 2 pi I over 3 n squared or something like that.
Yeah, there's an n square. That's what I'm trying to say.
2 pi over 3 n squared. No, I think it should change. It should change by 2 pi by 3 as n changes by 1, right?
Okay, that's the. So let me show you this. Here it is. I think I can explain everything. This is the what I call macroscopic part, including the real and the oscillatory part. In addition to this, there should be 2 pi I times just the charge. Small. So okay, this is the action. Now you do a Fourier transform. Okay, but in fact there should be another small piece, which is the rapid oscillation, which doesn't depend on rank. But what I'm trying to say is that there's a phase here to this action which depends on the rank square. And that's the thing which is causing the macroscopic oscillations.
Yeah, and I'm saying if you do normal thermodynamics on that will lead to a chemical potential of order 1.
That's right, because in the gravitational units, because
yes,
in front of this there'll be an n square times the gravitational charge. That's right. And the n square scales out and you'll get an order 1. That's absolutely correct.
No, I mean, in field theory units, it leads to chemical potential that is order 1 without an n square. No scaling. It's like temperature is order 1 at Hawking page.
I agree with you. I just give you a proof of why that's the case. Yes. Mm-hmm.
Yes. Okay, great. The other chemical potential you told us about was also, if I understand right, of order 1.
That's right. So the other chemical potential is just, it's just, if I write down the formula, excuse me, d of n, maybe I just go back. A long way, sorry, but here it is. The other chemical potential is you just change tau to tau plus 1. It's exactly that.
Excellent. So both are order 1. So they add up in the same order. There's no difference in n square between these two chemical potentials. That's what
no, but that's right. That's right. And what is your question now?
I just wanted to confirm that. I thought at the beginning you were saying that there were 2 different scales of chemical potentials. I misunderstood.
No, what happens is that the first one is a shift. So it doesn't, the first one is a shift. So you can just scale it out as a rapid
Yes, the
oscillation.
first one is rather trivial. The second one is not. Is what I'm.
Yeah, I would say it's just a constant shift, and so you can just scale out the rapid oscillation.
But even the first one carries information. Tells us
Of course,
that the
of course.
number of bosonic minus number of fermionic states changes
That's correct. That's correct.
on the scale. So both are physical of the same order.
Mhm.
Do you agree? Or one? Yeah, I have no question. I just wanted to confirm.
Yeah. So the first one is a shift of tau to tau plus 1, and here it's after minimizing it, the potential will also become of order 1. That's correct.
Yeah. Thank you.
So I don't think about it in terms of, so it confuses me to sort of minimize first before comparing these two. If you want to, yeah.
Okay. Thank you. Yes.
Sorry if I said something which is not correct earlier. Okay, so these are the new Cardi-like limits. And I just want to make 2 comments, namely that in ADS 3, so this kind of a situation that you have all these many saddles is not very exotic. In fact, one has seen the same structure of m comma n on a lattice with GCD equal to 1 in ADS 3 and in CFT2. So if you can write a CFT2 elliptic genus exactly in this kind of an expansion, there you have an exact formula, and you know that there are no other saddle points, and there each term has an interpretation in terms of gravity. This is the Malder-Sena-Strominger family of black holes, and here we don't know what these things are. Okay, we can predict some properties of it, but we don't know what these things are. Okay, then that finishes my discussion of part 2. There's a very short part 3. This is just comment saying that everything can be lifted to sort of bigger set of theories and including flavor potentials and so on. I'm going to skip this. Okay, now I'm left with 2 or 3 slides about this lore of graviton versus black hole, if you allow me that.
Please go ahead.
Okay, so let's see. So let's go to some basic ADS-CFT. So at infinite n, so this is, we were taught this in some basic courses, that single trace, let's stick to BPS operators, single trace operators are the same as single graviton states in the bulk. So the one natural thing you can say is that at infinite n, multi-trace operators should be multi-gravitons. This statement needs a bit of clarification because, you know, when you say multi-gravitons, in principle, you can also, multi-traces, you can also have an infinitely large trace. But if you take n strictly to infinity first, then this is correct. And this was sort of spelled out in this very nice paper following these earlier papers. All right. So Gautam, this is what I meant by the lore. Okay, that in this paper of Chang and Yin, they actually explicitly built the set of Yang-Mills operators which are in one-to-one correspondence with multi-gravitons. These are nothing but just the sort of, this is just group theory essentially, but they do it in a very nice way. Okay?
What are the conjectures at finite n?
I'll just say in a second. Okay, so that's what they did. And in this paper, what they conjectured is that, so if you start at infinite n and start reducing n, then you can ask, do new operators come in? Either new operators or some do operators go away because now you have relations and so on. And there was a conjecture that this does not happen. Okay. So Gautam, this is what I meant by the law.
Yeah,
so 1/16
I know that, you know, I know that in the context of
1/8 BPS.
Yeah, 1/8, 1/8 up to 1/8.
Yeah. So this is very nice work of you and Imani, who also construct some operators of that type. That's correct.
Yeah, I mean, and the group theory of that was you know, worked out by Corley, Javicki, and Ramgulam, where they look at this particular combinations of multi-trace operators, and in which the trace identities are incorporated already, and those operators correspond. Yeah, okay. So the limit that you were talking about here is n equal to infinity, and basically the trace identities don't come into play.
Yeah. So at n equal to infinity, there's no issue.
Yeah.
But so it's not a lore, it's a statement.
Yeah.
But then at finite n, the question is what happens.
Right.
Sorry, Samir, the conjecture at finite n is that this does not happen, that no new states come in, or no relation, I mean, no states go away. Is that the conjecture?
That's what I understand. Please correct me if that's wrong, because
But that
it's
would
not
make, in particular, the index independent of n, right? If I understand correctly.
precisely my point. Okay, so this seems to be in complete contradiction with what I just said in the last 1 hour.
No,
Okay,
if I understand right, I think what they were saying was that there were no new states. They weren't saying that trace identities don't kick in. That the basis, that the multi-trace basis of graviton operators was, once you include all the trace identities, was the right answer.
Okay, fine. So then, as I said, I don't want to misrepresent this paper. I've not, and I don't want to unpack this paper either. So let's just ask ourselves this question: what are these operators? Okay? Is it are they gravitons or are they black holes? But I mean, if no new states come in, that means, doesn't that mean that that this graviton index would be an upper bound?
Yes. So
okay.
I mean, they were saying that, I mean, I think Chang and Yin were saying that they thought that there was a supergravity correction to the index.
Fine.
That the supersymmetric black holes were lifted.
Right.
That the index does not capture the backward entropy.
That's exactly, okay, so good. So maybe I didn't say it in a very sharp way. What you're saying is even worse than what I was saying, in some sense, that the index, the index can at most have gravitons, something like that.
That's right.
Okay.
So I think this accounts for all of Gautam's giant gravitons, for instance, which would be essentially some trace identities on these.
Okay, fine. Okay, so at most will be even reduced. But what the point?
Sorry. So the conjecture is that dn is a decreasing function as a function of capital N. Is that the conjecture?
Yeah, and a very particular decreasing function, in the sense that you take the set of multi-gravitons, include trace identities, compute the index of that space, and that's the answer.
Yeah. Okay.
Okay. So just to make sure I understood, because Shiraz, may I confirm that the conjecture as you stated is in stark contrast with the existence of black holes and what I've been saying.
Yes. I think their point of view was that in the disagreement between field theory and gravity, it's gravity that's wrong.
I understand. So this is one reason I started by analyzing the gravity. These were the speculations I was saying, that perhaps the black hole doesn't contribute, etc., etc. So I wanted to sort of sharpen that first, which is exactly why I started by at that.
At least this is my understanding of the paper. Yeah.
Okay, but I've also heard this from other. I'd heard this from other people, which is exactly why I started from gravity. Okay, so this we already saw that. So there's some sharp tension. So here is the graviton gas, and here is the black hole. So what is going on? So here are some experiments. So here is the charge n, and here is the degeneracy as a function of the rank, d2, d3, d4, d6, and the last row is the index of the multi-graviton gas. And what you see is that the index is equal to the index of the gravitons up to a certain number, which is exactly 2 times rank plus 1. Okay, you see that this is in blue. It's 5, 7, 9, 10, etc. And after that, there is a deviation. Okay. Now, here is a plot of the deviation. So these are sort of intermediate energies, what I've shown you right now. The red curve is the graviton gas, index of the graviton gas, and these ones are n equal to 2, 3, 4. Okay, the SuperYang-Mills index. And you see, so at very small charges, what you see is on the table. There's an agreement, you don't see it on the graph. Then there's a disagreement, there's a dip actually. If you see here, if you look at absolute values, the values of the index is smaller than the multi-graviton, the dip. And then there's an increase, and here, for large charges, it agrees with the black hole prediction. Okay, so again, this table is very small charges, this graph is intermediate charges, and this is sort of the large charge theoretical prediction. Okay, so they're all continuously connected. And this fact you can prove, and this is what I did in my paper. So what the way to do this is
So, sorry, Samir, just to confirm, the counterpoint to the conjecture would be the later part of the graph, right?
later
Where
part,
it's going
exactly.
up.
What I want to show is that so because of my sort of other calculations, CARD and large limit, let's say CARD even, I'm convinced that there is a black hole state growth of states, but there is some truth to this fact that, I mean, there's absolute truth to this fact that n equal to infinity, something that multi-traces are multigravitons. So when you start decreasing n, there must be some truth to it. And the question is, how do these two get reconciled? Okay, that's what I wanted to explain. And you know, these experiments are very, very useful. So here you can see up to 17, but in the paper I give you numbers, but here is the graph, which shows you the explicit sort of interpolating function. Okay, and I have more comments about that later if you want. But that's what I was trying to achieve here. Is it clear? Abhijit, is that okay?
Sorry, yes.
All right. So now what in my last slide, I'm going to show you how to prove this. And that sort of brings me to something which I'm quite excited about. So I want to show that this phenomenon actually is I want to prove this phenomenon. Right, this is my last slide. So you start with this index function. We have this integral over unitary matrices, exponential of this infinite set of terms. Each one has a u and trace u dagger. We first expand it out, expand the exponential. So you'll get some infinite series, each term having some string of trace u's and string of trace u daggers. Now you expand this string of trace u's in the un characters. Okay, and there's a classic formula due to Frobenius who says how to do that. It says how to do that, and it says that in particular it says what the coefficients are. So remember that the characters of un are labeled by partitions of n, lambda, and lambda also labels the characters of the symmetric group Sn. Okay, so to every string here, you associate a certain partition P, okay, which you think of as a symmetric group element. Remember, let me just remind you all. For the symmetric group, the partitions play two roles. One is that it labels the cycles themselves, okay, the elements themselves. And secondly, it labels the characters. These two, it's a complete accident which holds only for the symmetric group. Okay? So P is the cycle, and lambda is the character. Okay, they're both partitions. So that's the Frobenius formula, and tells you that in particular there's a restriction that the length of the partition should be less than or equal to n. It just says that the Young tableau cannot have more than n rows if you start with un. Okay, that's fairly intuitive. Okay, so you take this formula for trace u, you write another formula for trace u dagger, which has a similar thing with chi of u dagger. Then you integrate over u, and using the sort of orthogonality relation of characters of un, you get this formula for the index purely in terms of characters of purely in terms of partitions. Okay, and this single letter trace. Okay, now there's no more un here, right? All these are the definitions. And now, if n is infinite, then this restriction that the length is less than n doesn't hold, and you have to sum over all partitions. When you sum over all partitions, you use the other orthogonality relations of characters of Sn, which says that this coefficient here is also 1. Okay, this is the sort of what is called the second orthogonality relations. So this becomes 1. So you get a very simple formula of only one sum over partitions of this single letter partition function, and addressed with P, and that is an infinite product. Okay, that's a standard calculation. And that infinite product, if you write out, you'll find that that's exactly equal to the multigraviton index entropy. Okay. And so this proof was for n equal to infinity, but for finite n, you can also go through this proof. This is what I did in this paper in May. And you can show that exactly up to charge. So the fact is that the index starts with x squared, and because of that, exactly up to charge less than or equal to 2n plus 1, the same proof holds. Okay. And therefore, this phenomenon that we just saw experimentally is actually a truth. Okay.
Wait, you're just saying that the first place where a trace identity can kick in is when there are n letters, right?
Exactly. Which is not at all surprising. I should say that so just to respond to that, it's what is interesting is the pattern that there's a bit of a dip. So it means like, there's a question of identities versus new states, and two phenomena are going on, and we have to unpack that. I haven't done that. I want to say that this last formula was actually understood in the original papers, was written down in the original papers, but I think they gave a slightly different interpretation. Okay, so that brings me to this Outlook slide. I think I've talked a lot, so maybe I'll just stop here. Thank you very much.
Thank you very much, Samir, for a very nice talk. I would request everyone to please unmute and thank Samir. Questions? Maybe we can keep this session brief, as we had many questions during the talk.
I'm happy to go on if you want. I mean,
okay.
Not even lunchtime, but it's
mind,
for you guys. So
okay, good.
Let me stop sharing. Well, let me keep it in case you.
No, do keep it. I think it's better.
I guess most people have left anyway.
Samir, I just wanted to understand better the proof. The proof that the saddle point of this non-holomorphic theory is relevant. Okay. So what I understood was that you could deform the contour in the holomorphic part, holomorphic extension to this contour, but there was nothing special about that contour. Then you produce some other extension which is non-holomorphic, for which this contour was a saddle point. I didn't understand the therefore after that. Why?
No, sorry. That's one step. Maybe you said it implicitly. The second step was that the value of the meromorphic action on this new contour is equal to the value of my deformed action at that contour.
Yes, that, and then the third observation was that this contour was a saddle point of the deformed action, non-holomorphic action. I don't understand why these three steps together tell you that this is a dominant contribution of the original action.
It's a saddle.
Yeah, please.
I don't know about dominant, but it contributes.
One of the saddle points of the original. Yeah. I mean, I don't understand at all why this is a special configuration. I'm missing something elementary, please.
So I would say it like this: that let's do everything in terms of the deformed action. I'll say that there are saddle points in the complex plane, and there's a certain contour deformation which goes through that saddle point, and now you have to justify why the value of the integral along the original thing is equal to the value of the integral along the saddle point. And to justify that,
we start with the deformed action at all.
I mean, that's my choice, right?
I could have chosen another deformed action. I would have got new saddle points, different.
Yeah, if you do that, and if you do all the steps carefully, it's very difficult to do that. The choice that I made had very special properties, but indeed, I think that if you do that and make sure of all these steps, which each of these steps are not trivial, then you would also get the same answer.
Yeah, please go on. Just give me a logic. I don't even see why it's relevant that the two actions are equal. That the action of the holomorphic theory and the action on this contour, that the action in the holomorphic deformation and the action in the non-holomorphic deformation are equal. I don't see why that's relevant logically to your conclusion. So please tell me.
Yeah, maybe I can just ask related to it. Instead of a path integral and so on.
Yeah.
You have. I mean, I have the same question as Shiraz has, and I'm not quite able to understand the manipulations that are being done here. Would you have some toy example of a complex integral? Forget about path integral, in which you can do such things, and you can get a good estimate of the original integral.
Yeah, my referee also asked the same question. So this is really it's not a path integral. Firstly, so let me try to say many things. So firstly, it's not a path integral. It's just an integral that I'm talking about. I've already localized it to some n-dimensional integral. You can even, right? Now, the fact is that I don't have an exact formula. So it's hard to, I don't have an equality in terms of saddle points. I don't have an equality that the sum over saddle points equals the function. So it's hard for me to numerically check this.
But even the rough intuition, sorry.
Yeah, I'll answer in a second. I was just responding to Gautam. So that's why it's difficult to do that. Now, again, let me just try to repeat what I say, and maybe you tell me what is wrong in the logic.
Yeah, please use the word therefore somewhere.
Okay, so you have an original integral to do, and you rewrite it in terms of the deformed action. Okay, so by construction, those two values are the same. You find a point in the complex plane, which is a saddle point of the deformed action, right? And there's a new contour which goes through the saddle point, okay? And I will show you that the values of the integral along the original contour of the deformed action is the same as the value of the integral along the new contour which passes through the saddle point of the deformed action. I will show you that later, but if that is true, then or therefore, I have locally dominant contribution to the original integral. So are you happy with that or not?
So you say that the value of the path integral of the original contour of the deformed action is the same as the value of the integral on the new contour of the deformed action. That's
exactly
what you're saying?
like, yeah.
So the deformation, the change in contour didn't matter, you're saying?
Exactly, yeah. So that's what usually happens for holomorphic functions, right?
Yeah, I mean, the correction factor is the Cauchy-Riemann part that you pick up in the bulk, which is
Exactly.
vanishing.
So I'm ignoring wall crossing and things like that. Let's forget about all those things. Let's say there's no residue.
Yeah, okay, fine. But this, you would have, there is some part, some region that is enclosed by two contours.
Exactly.
And the difference between these two a priori would be Cauchy-Riemann.
Exactly, and that should be 0. What I'm saying is that in this case, it's a contour integral of, well, in what I just said half a minute ago, it's an integral, line integral of a non-holomorphic function. But then the next step is to show that that integral is the same as the line integral of a holomorphic function, therefore it's 0.
I'm sorry, Samir, but first I heard you say that the integral on the original contour was the integral on the deformed contour, all in terms of the new non-holomorphic action.
Yes.
So
first let's do that.
This is not even a saddle point thing, right? Then you can just work with the new contour and you get the exact answer. It's not like you have to sum over saddle points or anything like that.
No, except that it's very difficult to do. But yes, in principle, you can do that. That's right.
Okay, fine. So you've now proved a mathematical identity saying, and the original integral of the deformed model was the original integral of the undeformed model, right?
Yes.
Okay, so you proved a mathematical identity. You say that you can now move to some new contour of the deformed action. Which is this new contour, by the way? It's any one of these saddle points?
For each saddle point, we have to construct such a contour. Roughly what you do is you stick to the original contour as close as possible. Then near the saddle point, you go up and you come down, and then you show that these two sort of cancel. Therefore, the dominant contribution is only near the saddle. And then you have to make some estimates about the width. But
doesn't this then tell you that every saddle point contributes the same? Because you're saying every saddle point contributes the same as the original contour.
No, so exactly. So here's where you have to be more careful, because so you can ask what happens for meromorphic functions. Let's think of what happens for meromorphic functions. Suppose there are more saddles. Okay. Suppose there are multiple number of saddles. What happens is that this argument breaks down because it's not true that what you ignored can be ignored. What you have to do then write the contour in terms of pieces. Okay, this is some Picard left shade or whatever basis you have. You have to write it in pieces such that it's equal to sum over saddle points. Right? Just think of what happens for meromorphic function.
Right. So can you just state the theorem you proved again? It was not that the original contour was the answer over the original contour in the deformed non-holomorphic model is exactly the same as the integral over the deformed contour of the non-holomorphic model? Have you proved that as an exact statement or something else?
So I have done what we do for holomorphic. Let me try to say it this way. So the procedure for holomorphic functions when it has multiple saddle points, right? I'm just following the same procedure.
Right. So what is the statement then? What is the relationship between these two contours?
The statement is that the integrals are the same. That's the first part of the statement. The integrals really are the same. And the second part of the assumption, which is clearly not true, and therefore you need other saddle points, is the fact that the whole thing can be approximated by a local Gaussian term. This is what you do for regular saddle point method either, when there are multiple saddle points.
But if the integrals are the same, doesn't every saddle point have to contribute equally?
You could have asked the same question for holomorphic functions. And the answer is that this approximation is that the Gaussian approximates the full integral is not true.
I see.
Right? Usually what you do for holomorphic function is that you deform it here, and then, I mean, the correct way to do is this, you have to write a basis of contours.
Yeah, there's Lefschetz symbols.
That you know that the thing decays and therefore the approximation is correct. That's the part I haven't done. That's the part we hardly know how to do in any sensible, any complicated theory. We only know for toy examples. So therefore, the only thing I'm really proving is that my saddle points contribute in the same way as they would if it were a holomorphic function.
Okay. Okay, I understand better. Thank you.
Okay, thank you.
But nevertheless, the thing that you said you will say later, why the two integrals are the same, that you haven't yet said, right?
So okay, this I don't want to do it here. This we can look up the paper. As I said, I can tell you in words, but if you want the formulas, we'll have to do it carefully. Basically, imagine a one-dimensional integral like Gautam was saying. Take a one-dimensional integral of the complex saddle point. The contour that we choose is like this. You keep the original integral until you hit the x value of the saddle point, minus epsilon. You go up. Oh, sorry. You wanted to ask why is this? You wanted to show why is the values equal or why the contours are equal?
No, why is the integral over contour C1 is equal to integral over the contour C2 for integrand, which is not necessarily a meromorphic function. I mean, for a meromorphic function, of course, I understand that you can deform contours.
Okay, so this is the same as Shiraz's question. Then is the fact that on C1, the integral of my function is the same as the integral of a meromorphic function, as well as on C2 with an approximation. And therefore, and for a meromorphic function, I know that the integral on C1 equals the integral on C2. Therefore, for my function also, I know the same.
I see. I see. So, okay. I mean, on C1, this is true because your continuation will just come down to the original integrand
right?
itself.
Yeah. So it's the C2 exactly. C2 it's non-trivial, so that needs a calculation, and the calculation is as so that we did in the paper, or I can tell you, or I can tell you now if you want.
I see.
And were all these identities, you said at some point they were true at large n, or were they more precise?
Yeah, so let me say exactly what is needed, why large n is needed. And I have a feeling someone smarter than me can actually make this into finite n. So this is the real axis and that's the complex saddle point. So you go like this, you go up to the saddle point x minus epsilon, you go vertically, take a small vertical contour, small horizontal contour at that height, hitting the saddle point, you come down and go that way, right? So the rest of the contour, is already equal to the original one. So you're only left with this little rectangular piece. These two, you argue, cancel each other. I think, I forget now, but those two don't contribute for some reason. Therefore, you only have to argue that the value, so now what? So what I argue is that for a small enough epsilon, the value on the top horizontal piece of the meromorphic action is the same as the deformed action. But then what? So then think of how we do the saddle point approximation. If you want to do the saddle point approximation, it's not enough that the value is equal. You want to do a Gaussian integral around that. Okay, that Gaussian integral has a width, right? That width should be large enough that so there's an n in front of the action, large n in front of the action. So that width cannot be too small. Otherwise, it's not going to be picked up by the Gaussian. So you'll get 0. So that width has to be, can't scale to 0 as n too fast. But it can't be too large because my approximation then breaks down. And then what you can show is that you can make the width of order, I think it's 1 over n or 1 over square root of n, I forget now, okay, such that both these conditions are true. Is that more or less clear why I need large n?
In the vicinity of the saddle point of this non-meromorphic function, if the integrand, is it the statement that it looks like meromorphic function there in that neighborhood?
Yes, exactly.
But then, because this notion of saddle point is also a very local notion, why then this doesn't become the saddle point of the, is that where this 1 over square root and etc. important?
That's also, let me think. That's a good question. I'll have to get back to you on this one. Yeah, this 1 over square root of n was certainly important because you needed it to be small enough that the two so the approximation breaks down. You can just see it on the computer. Okay, and the question is, yeah, I think that's exactly right. What you said is exactly right. That's right.
In particular, the derivative vanishing is not true for one but true for the other, right? So
yeah,
in that sense,
but you can
at
ask
least,
what is, so for the meromorphic action it doesn't vanish, but you can say by how much. And that you can scale to 0, still keeping the saddle point. So maybe the whole argument can be rewritten in terms of holomorphic. Maybe.
okay.
So you're saying it's an approximate saddle point of the meromorphic action?
Maybe.
Yeah, that roughly is
that's
how,
what Abhijit was driving at.
yeah.
So for
And
small
that,
tau,
the error is controlled by that 1 over this thing. That's why you need large n.
So for small tau, that is true.
Mhm.
Yeah, the reason I sort of like this function is because it simplifies the calculations enormously. So all of calculating the action for the meromorphic action with the meromorphic integrand is not at all easy. And there seems to be some sort of reason why this. And this function is not arbitrary. It obeys all kinds of differential equations. Maybe there's another proof of what I said, using the fact that it obeys a certain differential equation. You don't, I mean, other functions apart from holomorphic functions obey no residue. So there's some differential equation usually behind it. So it need not be the Cauchy-Riemann equation. And this one also is known to obey some interesting differential equation. So maybe that's another way of saying why it works. Yeah.
And also, if the answers match on, the saddle point actions on each of these nm saddle points, if they match up with the Bethe-Ansatz solutions,
yes.
then is there a way to make this procedure same as the procedure there directly, at the level of the integral itself?
No, I don't think so. I mean, I think there's a deformation.
Yeah, sorry.
Yeah.
I asked this because there was no non-holomorphy there.
There was no absolutely, right? So there was completely analytic.
So the fact that these are agreeing, it's a bit discomforting because you have an explicit factor of Z2 and so on. I mean,
no, I would say it's a deformation. So my intuition for this is that there's a Q deformation. Usually these things are just Q deformations. Right? I don't see why it should. Why is it discomforting?
Sorry, Sami, just totally clear. If I take one of your configurations and I do the holomorphic deformation, I should find the saddle point equations being obeyed to subleading orders in 1 over n. Is that what you're saying?
I think that's correct. Again, if you want, I'll get back to you.
Great, but saddle points are a large n notion. Then you're saying that it's a saddle point of the holomorphic.
Yeah. So there is something to be said there. Yeah, I need to. At some point of time, I've done a sort of calculation of the meromorphic function itself. I think it's best answered if I pull out that calculation sometime and try to sort this out rather than.
Okay, thanks a lot.
Rather than a theoretical reasoning of what should be going on, which I'm not very good at. But apart from that, is the if you don't want a relation to a saddle point in the meromorphic language, is it clear what I'm doing? Is it?
It's clear to me now. Yes, thank you. But of course, your proof of this vanishing of the bulk integral was that it was the relationship to the meromorphic integral.
Yes.
Right. So it sounds suggesting quite directly as we've been saying, as Abhijit was saying also, that just directly, that you might be able to do everything directly with the meromorphic.
Maybe true.
Okay. Yeah. Okay. Thank you.
Yeah. It might be a little more. Okay, I'll have to think about this because there's also an issue of the value of the action and the value of derivatives and an actual shift of the configuration of eigenvalues itself. So I'm pretty sure that the uniform distribution, I mean, we all know the uniform distribution is not does not solve the saddle point equation of the meromorphic action. And the question is, does some deformation of that distribution solve it, right? Because if the uniform distribution solves it approximately, then you could imagine that there's a new solution which solves it exactly. So yeah, there's something to be understood there.
So one more question, Samir. The saddle points that you had produced with this matrix model all had action which proportional to n squared, right? Except for the gas of gravitons.
Good.
Then is there a way to somehow get giant graviton states also with this matrix model?
Yeah, Francesco is also asking me this question. I don't know. It's a good question. By the way, not everything goes as n squared. So you see that only when m plus n is 1 or 2 mod 3, 1 or minus 1 mod 3, it goes as n squared.
Yeah, I mean either n squared or 1, right?
Yeah, exactly.
But you would yeah, okay.
Yeah, so you're asking if there are other saddle points which, yeah. So let me say one thing which may be relevant is that let's go back to this. Let's go back to this. You can ask, can I approximate this data by a sum over saddle points? Of course, what you're asking is a very subtle thing. It's somewhere, some linear in n, somewhere here, right? But I'm trying to sharpen my numerics to see if you can just sum over gravitons.
You have to get n somewhere, right?
Sorry.
You have to get n somewhere if you want to model.
So some n instead of n squared. So I'm just trying to sharpen my numerics to see if I subtract the gravitons, then I'll get rid of some part of this. Then I'm left with a more or less periodic oscillation, and the question is how periodic. It's a hard numerical question because what you're asking, because you're in a regime of small charges. So who knows? Maybe it.
Okay.
I should also say one more thing, that if you go here, if you're on this axis, this vertical axis, you can ask why do I not? This was the axis where the original papers were on. Okay, I shifted by some quantity, and you can ask why. Is it true that the free energy has n squared growth or not? And for me, somehow that's a very confusing question, because that's a very subtle question, right? Precisely because of this macroscopic oscillation. It turns out that's exactly where the sort of Stokes phenomena happens. And there can be two macroscopic things which cancel, so that even the free energy is not n squared. Generically, the free energy is always n squared. And in the microcanonical ensemble, such subtleties don't happen. You just have some numbers, maybe with some phases. Just ask whether they grow or not.
Can't you ask this question numerically in your numerics?
What question? Whether this is 0 or not?
Yeah, whether this thing
I'm saying it's at this, your calculations were absolutely right. I'm saying the reason it's right from this point of view is very subtle. Generically, the free energy goes as n squared.
Right. I understand, but could we confirm my calculations through numerics? Just compute the index. Compute
index function as a function of this. Yeah. So I sort of did that with some bad numerics, and it was showing that. But I'm happy to try to polish that if you want, if that helps.
So what are these calculations, Shiraz?
I mean, he's just evaluating the matrix integral at real chemical potential.
Oh, okay.
Just calculate it here. So it's subtle because you have two large things and you have to subtract them. But so that's why the numerics have to be polished. But when I first did it, it's true. But if you want, I'm happy to do that.
I mean, if it's easy, it would be great to be totally sure, right? Because we made so many mistakes. Maybe this was also wrong somewhere.
No, I think that's correct. I think it's just a very non-generic, very special slice that was chosen.
Right.
I mean, I can bet on it that's true. I mean, now I have a theoretical understanding of why that's true. So numerics must work, but I'm happy to continue.
Sorry, what is the theoretical understanding?
It's the fact that there's a perfect symmetry to this problem around this axis, and I know that the largest contributions are this pink one and this yellow one, and I know the phases. And I know that they cancel exactly.
But the subleading part may not be n squared, it could be n, right?
Yeah, so that's the thing. That's exactly the thing to check.
Yeah.
That's exactly the thing to check. So that's why it's subtle, because it's,
Yeah.
going to n. Yeah, even for the index function is actually much harder than plotting the integers, because integers are, you can use lots of tricks. Index function is it's a continuous thing of the plot, and even for the integers, it took me quite some effort to get up to n equal to 10 or something.
Sorry, just one more question. As a function of tau, if you ask what is the dominant saddle point, there will be somewhere where assuming your saddle points are the only ones that are there, there'll be somewhere where the black hole dominates. There'll be somewhere where the gas dominates, but there will be presumably places where other things dominate. Right?
That's exactly what you're seeing on this slide.
Right. And so is there ever just a direct transition between black holes and gravitons? Or do other things always... So blue is gravitons?
Blue is pure radius, yeah, gravitons.
I see. But somewhere in the middle of your curve, there's a transition to something else.
No, the transitions are only here.
So from black hole, you always go to gravitons, or you?
Well, except for So this is the part where I have less control, because I'm for various reasons. Precisely because of this interference, but so if you go like here, for instance, you might move from black hole to another saddle point. It's at every rational point. So for sure you'll hit a rational point here.
I see. So you will sometimes go to some other saddle point.
Yeah, but that's only if you're very close to the real axis and move in the horizontal direction. So that's why I showed you this picture first. Here there's just black holes and radius.
I see. So at reasonable values of chemical potentials, you say that there is the dominant saddle will always be either the black hole or the graviton gas.
That's correct.
Okay.
So I might have forgotten some questions. I might have made promises that I'll get back, but I wrote down only all the things I wrote down. I cancel because I answered
everything.
If that's the case, please tell me. Sorry, I didn't hear you.
I think you answered everything.
Okay.
I can't remember a question.
Okay, up to this numerics, but that I can't tell you tomorrow. That
Okay, any more questions? If not, let's thank Samir again for a very nice talk and being so very patient with the questions.
Thank you for your time.
Thanks, sir.